Hi all, today we will discuss few of the problems related to sampling theorem and pulse code modulation before moving on to the next concept, which is regenerative repeaters. So the first problem statement goes like this: a signal M of t band limited to 3 kHz is sampled at 33 1 by 3% higher rate than the Nyquist rate. That means it is 1 plus 1 by 3 times more than Nyquist rate. Sampling rate is given as 1 plus 1 by 3 or 1.33 times of Nyquist rate has been used to sample the signal, which is having a bandwidth of 3 kilohertz. So it is band limited to 3 kilohertz, means bandwidth omega is 3 kilohertz. Now next, the maximum acceptable error in the sample amplitude, that is the maximum quantization error, is 1% of peak amplitude MP. If you consider peak amplitude as 1 volt, then the error will be 1% of that 1 volt, that is you can say 0.01, and the quantized samples are binary coded. Now what we have to do, we have to find out the minimum bandwidth of channel required to transmit the encoded binary signal, and for that also, if 24 such signals are time division multiplexed, we have to determine the minimum transmission bandwidth required to transmit the multiplexed signal. So first thing is, we have to calculate the bandwidth for one signal, then bandwidth for 24 signals. So given, as I have already told, omega is equal to 3 kilohertz is been given. Bandwidth bt is given by n into fs by 2, where n is number of bits for representing each sample or each quantized level or each quantized level, where and fs is sampling frequency. Okay, now to calculate bt we require n, we require fs. Also we can find it by using the signaling rate, which is given by small r. That also will understand, which will be helpful for solving next few problems as well. Okay, so to calculate sampling rate, we are going to use the equation for fs. Fs is sampling frequency, it is nothing but Nyquist rate, okay, in the general case, but here 33 of 1 by 3% more than the Nyquist rate, which is 1 plus 1 by 3 times more the Nyquist rate, so it is 4 by 3 times more the Nyquist rate. And what is Nyquist rate? It is 2 times omega. So omega is 3 kilohertz, the bandwidth of message signal. Using this, what we'll get? We'll get fs as 8000 samples per second. Okay, in textbook and all it is given as 24,000 samples per second, which is wrong. To find out number of bits to be represented for each sample, we need to find out number of voltage levels, that is given by L. So this L can be calculated if we find step size. For that we'll make use of maximum error, which is 0.01, and we know that maximum error is given by magnitude of delta by 2. So we can find out the delta as 0.02 by substituting for maximum error, that is 0.01. we'll get delta as 0.02, which is our step size. And what is the relation between quantization levels L, that is capital L, and step size? Step size is always delta is equal to 2 by L. That means L is equal to 2 by delta, which will give you 2 by 0 to which is 100 levels. So 100 different voltage levels are going to be used in the quantizer. To represent these 100 voltage levels, how many bits are required? For that, as I have already said, this is the equation. Using this equation, we are going to get n is equal to 6.643. So we have to approximate this value to the next integer. So n will be 7 bits. So each voltage level in this particular quantizer is now represented by 7 bits, which is pulse code modulated signal. Using this, we can calculate the bandwidth. Bt is equal to 1 by 2 n into fs. So n is 7 bits, fs is 8000 samples per second. So the bandwidth required for transmitting the particular signal is 28 kilohertz. Now transmission bandwidth for 24 channel, this should be 24 different signals. For 24 signals is BTR is equal to 1 by 2 into R. What is R? R is the signaling rate, and it is given by this equation where R is equal to capital N multiplied by small n into Fs bits per second. N might be number of channels or number of different signals, whereas small n is number of bits to be represented for each sample, and Fs is the sampling frequency, as you already know. Now using this, we can calculate R, and substituting the value of R in the bandwidth equation for 24 signals, we are going to get 672 kilohertz as the transmission bandwidth. So it is directly proportional. Number of signals, if you go on increasing, required bandwidth also goes on increasing at the same rate. Now moving on to a second problem, which is been asked in the model question paper 2021 also. Here a television signal with a bandwidth of 4.2 MHz is transmitted using binary pulse code modulation. The number of quantization levels is 512. We have to calculate code word length, transmission bandwidth, and final bit rate. So what is code word length? Code word length is nothing but number of bits required to transmit each voltage level. So that is n. We need to calculate what? N. Transmission bandwidth means Bt, and final bit rate is nothing but signaling rate, which is R. We need to calculate R. We need to calculate Bt. We need to calculate N. Okay. Now given is the bandwidth of the television signal, which is 4.2 MHz. This is the message signal bandwidth, we can say, and number of levels we can have in this bandwidth is 512. So as we already know, L can be given by the equation L is equal to power n, and if we simplify by applying logs, we'll get n is equal to log L to the base 2. Okay, that can be written in this way also. So it is somewhat simplified version of the earlier equation. Now using this, what we get is n is equal to 9 bits. So each voltage level can be represented by 9 bits. Now to find out transmission channel bandwidth, it should be greater than n times omega, or 1 by 2 nfs. Both are equally correct. So using this equation, we are going to get 37.8 MHz as transmission bandwidth. We require at least 37.8 megahertz of bandwidth for transmitting this particular television signal. Okay, and as I have told, the code word length is 9 bits. N is what? Code word length. And then the final part of the question, here we need to calculate bit rate, which is R given by capital N into small n into Fs. So capital N is equal to number of channels or number of signals. So it is 1 because only one channel is there and one signal is there, correct? And number of bits is 9. Fs already we know, which is 2 times omega. Using this, we can write that the signaling rate must be at least equal to 75.6 megabits per second, or Mbps, the same thing which we generally use when we talk about data speed of our internet communication or mobile communication, correct? So that's all about the second problem. Going further, third problem, please solve on your own. So this is the answer for the third problem, and this one is the fourth problem. This one also you can solve. Moving further, fifth problem is important because here it has been asked in the model question paper again, and the question goes like this: a compact disc or CD records audio signals digitally using pulse code modulation. Assume the audio signal bandwidth to be 15 kilohertz. So bandwidth of the message signal is 15 kilohertz. What is Nyquist rate? The second part is if the Nyquist samples are quantized to L is equal to 65,536 levels and then binary coded, determine the number of bits required to encode a sample, that is N. We need to calculate Nyquist rate Fs or sampling frequency. Then we need to calculate N. Assuming the signal is sinusoidal, that the maximum signal amplitude is 1 volt, determine the quantization step and signal to quantization noise ratio. So we need to calculate delta and then signal to noise ratio at the output. Okay, given is, as I have already indicated, it is omega is equal to 15 kilohertz, which is our signal bandwidth or message signal bandwidth. Nyquist rate is Fs, which we need to calculate. The number of levels we can represent is 65,536. Need to calculate number of bits, delta, Vmax, or you can say MP, M of t maximum, whatever you name it, it is maximum amplitude of the signal, which is 1 volt. And signal to noise ratio in decibels we are going to find out. Okay, first A, Nyquist rate, which is very simple, as you already know. Fs is equal to 2 times omega, which is 2 into 15 kilohertz. You are going to get 30 kilohertz as the Nyquist rate, or 30,000 samples per second is the Nyquist rate. Number of bits, N is equal to log L to the base 2. So L is what? 65,536. So N you are going to get exactly 16. So 16 bits are required to encode a voltage sample. And the third point, where we are going to calculate what? Delta, that is step size, and delta can be given by the equation 2 times Vmax by L. So if we substitute, Vmax is equal to 1 volt, 2 by L is the delta size. So we are going to get delta value as 3.05 into 10 to the power minus 5 volt, or you can say 0.305 microvolt is the quantization step size. Okay, now coming to the signal to noise ratio, we have the equation as SNR in decibels is equal to 1.8 plus 6n, where n is the number of bits used to represent each sample. So it is 16, as we have already calculated here. Using this, we'll get 97.8 decibels as the signal to quantization noise ratio. Because we are using more number of bits, that is 16, we are going to get a very good signal to noise ratio. Okay, so that's all about the problems which I wanted to discuss with you. Thank you.